Good morning friends. In chapter 12 thermodynamics, already we discussed about the working of the Carnot engine and also the principle of the Carnot engine. Now in Carnot engine, Carnot cycle is completed in 4 reversible processes, 2 isothermal and 2 adiabatic reversible process. And already we derived the equation doing the isothermal expansion and also adiabatic expansion and also adiabatic compression and isothermal compression. First step, that means in Carnot engine a Carnot cycle is completed in 4 different steps. First step is the isothermal compression. During the isothermal compression, the work done by the gas is W1 is equal to Q1 is equal to mu RT1 ln V2 upon V1. Right? And the second step is adiabatic expansion. That means the whatever the gas is filled in a piston cylinder arrangement is adiabatically expand from step 2 P2 V2 T1 to the P3 V3 T2. During this process, adiabatic expansion, the heat is not exchanged. That means the exchange of the heat is 0 and work done W2. There is the work done by the gas. W2 is equal to mu R T1 minus T2 upon gamma minus 1. Gamma is the ratio of the Cp and Cv. Cp upon Cv. Okay. Now in third step, the gas is again the isothermally compressed. That means the temperature remains constant from step 2 to the step 4. But the exchange of the heat takes place. That means the gas releases the Q2 amount of the heat in the heat sink. Therefore, Q2 is equal to W3 because there is the work done on the gas. Work done on the gas to release the Q2 amount of the heat is equal to mu R T2 ln V3 upon V4, equation number 3. And now last, the gas is adiabatically compressed to obtain its initial state, step 1. That means P1 V1 T1 from P4 V4 T2. Therefore, during the adiabatic compression, the work done on the gas W4 is equal to minus mu R T2 minus T1 upon gamma minus 1. Here, there is the negative sign, so we convert into the positive. Therefore, mu R T1 minus T2 upon gamma minus 1. Now, from these two equations, during the step 4 and step 2 and step 4, the work done are same. But equation 2 represents the work done by the gas and that is the work done on the gas. Therefore, this work done is positive, this work done W4 is negative. Clear this thing? Already we discussed in earlier lecture. We described the 4 steps take place in Carnot engine during the 1 Carnot cycle or the 1 Carnot cycle. Okay. Now we are using this equation to obtain our next question. Obtain an equation of the total work and efficiency of a Carnot engine. Right? Equation of total work and efficiency of a Carnot engine. So first we obtain the equation of the work done. Total work done during the 1 Carnot cycle is equal to the addition of these 4 works take place during the 4 different steps. Therefore, the total work done in a Carnot engine in 1 Carnot cycle or during 1 Carnot cycle is W is equal to W1 plus W2 plus W3 plus W4. but W2 is equal to W4. Whatever the work done during the adiabatic expansion and during the adiabatic compression are same, but equation 2 represents the work done by the gas, and that is the work done on the gas. And W2 is work done by the gas, while W4 is work done on the gas. Therefore, W2 is equal to minus W4. Right? Okay. And also, W3 is also work done on the gas. And W3 is also negative. Also negative. Because there is also the work done on the gas. Therefore, total work done is W1 minus W3. W1 minus W3, there is the equation 1. Okay, so here the W1 and W3 are the work done during the isothermal compression and isothermal expansion. Okay, during the isothermal process, the work done is same because the temperature is remain constant. Therefore, the change in internal energy of a system is 0. So from first law of thermodynamics, W1 is equal to Q1 and W3 is equal to Q2. So we can add, there is the Q1 minus Q2. There is the total work done in a CARNOT engine during the CARNOT cycle. One CARNOT cycle. Clear this? Again, total work done in a CARNOT engine during the one CARNOT cycle is the addition of these all works. W is equal to W1 plus W2 plus W3 plus W4. But W2 is equal to W4 and W2 is work done by the gas, that is positive, and W4 is work done on the gas, that is negative. Therefore, W2 is equal to minus W4. And also, W3 is the work done on the gas, that is also negative. Because there is the work done on gas. So using this concept, therefore the total work done, W is equal to W1 plus W2 minus W3 minus W2, that is cancelled, and W3 becomes the negative. Therefore W is equal to W1 minus W3. Okay. So W1 and W3 are the work done during the isothermal compression and isothermal expansion and isothermal compression. So during the isothermal process, the temperature remains constant, therefore change in internal energy of a system is 0. So from first law of thermodynamics, W1 is equal to exchange of the heat and W3 is also exchange of the heat. Therefore we substitute W1 as Q1 and W3 as Q2. So that is the total work done. W in a CARNOT engine during one CARNOT cycle in terms of the heat exchange. Now we are interested to obtain the equation of efficiency of a CARNOT engine. We know the equation of the efficiency. The definition of the efficiency of a heat engine, because the CARNOT engine is one type of the heat engine. Already we derived the equation of the efficiency of a heat engine. Efficiency of a heat engine is the ratio of total work done per cycle to the total heat absorbed per cycle. That means the W upon Q1. So here the efficiency of a CARNOT engine. Now, and efficiency of a CARNOT engine is N is equal to W upon Q1. But from equation 1, W is equal to W1 minus W2 upon Q1. Or in other words, there is the Q1 minus Q2 upon Q1. Therefore, 1 minus Q2 upon Q1. 1 minus Q2 upon Q1. That is our second equation. Substitute the value of Q2 and Q1. Therefore, efficiency N is equal to 1 minus Q2. Q2 is mu R T2. Mu R T2 Ln V3 upon V4. V3 upon V4. Divided by Q1 mu R T1 Ln V2 upon V1. V2 upon V1. Now listen, mu R cancel. Therefore, our equation is reduced to N is equal to 1 minus T2 Ln V3 upon V4 divided by T1 Ln V2 upon V1. Clear this? Now we are interested to find out the ratio of this V3 upon V4 and also V2 upon V1. That is our equation number 3. Now already we know that for adiabatic process, there is no exchange of the heat. For adiabatic process, the relation between the temperature and volume is Tv raised to gamma minus 1 is equal to constant. That is the equation for adiabatic process. Right? Now, here the adiabatic process takes place in step 2 and step 4. Therefore, for step 2, that means adiabatic expansion. Here the system goes from P1, V1, T2 to the P2, V2, T1. P2, V2, T1. Therefore, we take like this way, that is the step 2. Step 2, that is the adiabatic expansion. Here the system is going from P2, V2, T1 to the P3, V3, T2. Therefore, we can write T1, V2 raised to gamma minus 1 is equal to T2 V3 raised to gamma minus 1. Taking the ratio V2 upon V3, therefore V2 upon V3. Take the V3 in this side and whole power is gamma minus 1 is equal to T2 upon T1. T2 upon T1. Take the V3 in this side, T1 in this side. Okay. Now here the power is gamma minus 1. We are taking the root, both side root of power gamma minus 1. Therefore V2 upon V3 is equal to T2 upon T1 raised to 1 upon gamma minus 1. 1 upon gamma minus 1. That is our equation number 4. So thus we obtain the value of V2 upon V3. V2 upon V3 is equal to T2 upon T1 raised to 1 upon gamma minus 1. That is for step 2. During this step, the adiabatic expansion takes place. Again, we repeat, an efficiency of the Carnot engine is N is equal to total work done per cycle to the total heat absorbed per cycle. Already we know that W is equal to W1 minus W3. W1 minus W3 and total heat absorbed is Q1. But W1 is equal to Q1, W3 is equal to Q2. Therefore, Q1 minus Q2 upon Q1. Therefore 1 minus Q2 upon Q1. We substitute the value of Q2 and Q1 in this equation. Therefore efficiency N is equal to 1 minus equation of Q2 mu R T2 ln V3 upon V4 divided by value of Q1 mu R T1 ln V2 upon V1. Mu R is cancelled, therefore N is equal to 1 minus T2 upon T1 ln V3 upon V4 upon T1 ln V2 upon V1. Now we are interested to obtain the equation of efficiency in terms of the temperature. For that purpose, for adiabatic process, we are using this concept PV is to gamma minus 1 is equal to constant. Here, the adiabatic expansion takes place in step 2. That means the system going from P2, V2, T1 to the P3, V3, T2 state. Therefore, we are applying this equation for step 2. T1, V2 is to gamma minus 1 is equal to T2, V3 is to gamma minus 1. Take the V3 this side, V2 upon V3, gamma minus 1 is equal to take T1 in this side, T2 upon T1. Here the power of the V2 upon V3 is gamma minus 1. Taking the root of power gamma minus 1 on both sides, therefore V2 upon V3 is equal to T2 upon T1 and power is 1 upon gamma minus 1. That is equation 4. Okay. During the Carnot cycle, again the adiabatic process occurs in step 4. That is the adiabatic compression. Adiabatic compression. Here the system goes from P4, V4, T2 to the P1, V1, T1 state by the adiabatic compression. Right? Therefore, we apply for step 4. Adiabatic compression. Adiabatic compression. We apply this equation. There is also adiabatic. Therefore, T1 V4 T1 V1 raised to gamma minus 1 is equal to T2 V4 raised to gamma minus 1. That is our equation. Now this equation now not required, therefore I cancel it. Again take the V4 in this side, V4 in this side, therefore V1 upon V4 raised to gamma minus 1 is equal to T2 upon T1. T2 upon T1. Now again take the square root of power gamma minus 1 on both sides. Therefore V1 upon V4 is equal to T2 upon T1. Power is 1 upon gamma minus 1. Equation 5. Again we are applying the same formula for the step 4, because step 4 the system is adiabatically compressed from state P4, V4, T2 to the P1, V1, T1. Therefore, applying this equation, TV is to gamma minus 1, T1, V1 is to gamma minus 1 is equal to T2, V4, gamma minus 1. And we obtain V1 upon V4 is equal to T2 upon T1 raised to 1 upon gamma minus 1. Now, equation 4 and 5, the right hand side are same. Therefore, comparing the left hand side. Now, comparing equation 4 and 5. So, we obtain V2 upon V3 is equal to V1 upon V4. V1 upon V4. Thus, we obtain the ratio of the volume V1 upon V2 upon V3 is equal to V1 upon V4. Now, refer the equation number 3. We require the ratio in that form, V3 upon V4 and also V2 upon V1. So take the V4 here and V3 here. Therefore, we can write V2 upon V1 is same as the V3 upon V4. V3 upon V4. So both are same, V2 upon V1 having the same value of the V3 upon V4. Substitute in equation 3. Therefore, we obtain the equation of efficiency is 1 minus T2 upon T1. Because this part is same, so that is the cancel. ln V3 upon V4 is cancelled with ln V2 upon V1 because the V2 upon V1 is equal to V3 upon V4. Therefore, efficiency of a Carnot engine is eta is equal to 1 minus T2 upon T1. Right? Okay. Is the equation of an efficiency of a Carnot engine. So very easy, only the mathematical solution to obtain the equation of the efficiency of a Carnot engine. Very easy, but keep in mind the four equations already we discussed during the working of a Carnot engine. First for isothermal expansion, second for adiabatic expansion, third for isothermal compression, and fourth step is the adiabatic compression. And what are the work done by the gas and also on the gas, we have to keep in mind to derive this equation. Here is okay.